In this video we present some results from the method presented in our paper, which is titled GRIT, Fast, Interpretable and Verifiable Goal Recognition with Learned Decision Trees for Autonomous Driving. We show examples of goal recognition over time for specific vehicles and goals, and we also show how the interpretable learned decision tree is parsed. On the left you can see our first scenario, which is a main road with a turn-off to a side road. The red dots represent goal locations, the blue boxes with arrows represent vehicles, and the blue box next to the vehicle shows goal probabilities. On the right, the decision tree for goal G2 is shown, with the tree parsing shown in blue. The values at leaf nodes show the inferred goal likelihood, calculated as the product of weights of traversed edges multiplied by 0.5. From the decision tree on the right, it can be seen that the goal of turning left, G2, is given a very high likelihood of 0.999. This is because the vehicle is in the correct lane for turning left, given weight 1.91, and is not angled to the right, given weight 1.05. The next scenario is an unsignaled crossroad with a vehicle approaching from the east. At first, the goal of turning right towards goal G0 is given a likelihood of 0.429. The vehicle then gently decelerates, which causes the likelihood to rise slightly to 0.564. As the vehicle moves closer to the goal location, the goal likelihood further increases to 0.993. Our third scenario takes place in a roundabout, with a vehicle entering from the north and taking the first exit towards goal G2. Although the first exit starts with a high goal likelihood, this is weighed by its low prior probability and the goal is given a low posterior probability. As the vehicle becomes close to the exit and starts turning, the goal likelihood increases to 0.999. Along with the likelihoods of other goals decreasing, this leads the goal probability to increase. One advantage of GRIT over other goal recognition methods is that we can formally verify that certain statements about the model always hold true, using an SMT solver. One example is the following statement. If a vehicle is in the correct lane for a goal, then that goal should have the same or higher likelihood than if the vehicle is not in the correct lane, if all other features remain unchanged. We ran verification for this statement for 47 goal-type pairs in 4 different scenarios, and the verification was successful in 43 of these cases. Here is an example of a case where verification was successful. The vehicle coming in from the west is in the correct lane to head straight on and reach goal G1. This goal is assigned a likelihood greater than it would be if the vehicle was in the incorrect lane. Here we show a case where verification fails. However, even when verification fails, the SMT solver provides us with a counterexample which can teach us about the way in which the model works. The vehicle we are interested in is again coming from the west, and the tree shown on the right corresponds to the goal G2, turn left. Although the vehicle is in the correct lane to turn left, it is angled heavily to the right relative to the lane direction. This indicates that it is changing lane to the right, and in such a case, giving a low likelihood to turning left is actually sensible.